Hello, and today's purpose of the day is I can identify linear, quadratic, and exponential behavior and write equations for the data. Analyzing functions. Let's review linear, quadratic, and exponential functions, their equations, and what the graph of each of those functions looks like. Let's start with linear. What is slope-intercept form for a linear equation? You guessed it. Y equals mx plus b. What does m represent, and what does b represent in the linear equation? M represents the slope and b represents the y-intercept. We can calculate m, or the slope, by figuring out the rise over run in the graph, or if we have a table of values, we can look at the change in y over the change in x. And so what that triangle means in front of the y and in front of the x is it means change in. And another word for that triangle with a mathematical term is called delta. So change in y over change in x is how we can find the slope, and we'll review that on the next slide. So let's look at what a graph would look like here for a linear equation. And what would the graph of a linear equation look like? You guessed it again, a straight line. So as you can see on the graph that I have drawn, I have a straight line, okay, and that red dot is represented by the y-intercept. So 0, comma b would be the y-intercept here. All right, let's look at quadratics. What is standard form for quadratics? Wow, you are just on a roll. You are correct. It is y equals ax squared plus bx plus c. What does the graph of a quadratic look like? Yes, it does look like a parabola, a U-shaped graph. And for analyzing functions and writing functions today for quadratics, we will specifically write them in the form of y equals ax squared. We're not going to worry about plus bx and plus c right now. All right, and last, let's look at exponential. What is the equation for an exponential function? You are correct. It is y equals a times b to the x. What does the graph of an exponential function look like? It looks like a smooth curved graph. As you can see, I have plotted the y-intercept, and we can look at this graph that I've drawn in. Is increasing to infinity and is getting very, very close to the x-axis, but will never actually get to 0. Determining linear, quadratic, or exponential data from a graph. So our example 1, we are going to graph each set of ordered pairs. Then from the graph, we'll determine if the ordered pairs represent a linear, quadratic, or exponential function. Please take some time right now to graph the points from A, B, and C and determine which function they represent. As you can see, I've graphed the following functions, and A was a quadratic function, B was exponential, and 3 was linear. So in the last example, we graphed data and determined what type of function we had. But now let's analyze data without graphing and look for specific patterns. So, assuming that x values are increasing by the same amount for a linear function, differences in y values are all the same. Assuming that the x values are increasing by the same amount for a quadratic, second differences in y values are all the same. And assuming that the x values are increasing by the same amount for exponentials, ratios of successive y values are all the same. So let's take a look at our 3 tables above. So with this first table, we can see that the x values are increasing by the same amount, increasing by 1, and let's determine what's happening with the y values. From -1 to 1, we are adding 2. 1 to 3, we are adding 2. 3 to 5, adding 2. So we are adding 2 each time in table 1, which means we are having differences in the y values. So this function would be a linear function. All right, let's look at the second table here. The y values are increasing, again, the same, going up by intervals of 1. But let's see what's happening in the y values. I can see here from 36 to 12, that's dividing by 3. 12 to 4, dividing by 3, and to get to 4/3, again, dividing by 3. But with exponentials, we want to figure out ratios of successive y values here. And so instead of saying dividing by 3, I want to say multiplying by 1/3. Multiplying by 1/3 each time. So I can tell that this function would be exponential. which then leaves perhaps a third table to be quadratic, but let's make sure that it will be quadratic. So again, x values are increasing by a common interval. They're all going up by 1, but in the y values, let's determine what's happening. From 32 to 18, we are subtracting 14. From 18 to 8, subtracting 10. From 8 to 2, subtracting 6, and from 2 to 0, subtracting 2. So, but the definition of quadratics for the y values is that we have common second differences. So that negative 14, negative 10, negative 6, and negative 2 were all the first differences. So now let's find the difference between those differences. So the difference between negative 14 and negative 10 is we are adding 4. From negative 10 to negative 6, we are again adding 4. From negative 6 to negative 2, we are adding 4. So those are common second differences. Again, the first differences weren't the same. Therefore, that's how we figure out the quadratic function. Now, once we have a table of data and we can determine which function it goes to, linear, quadratic, or exponential, we now want to write an equation for that data. So we have to figure out, again, not only what the table is telling us, but which part of each equation the variable means. So as we look at linear, y equals mx plus b, let's just recap. M, again, represents the slope. B represents the y-intercept. For quadratics, y equals ax squared, we actually are going to have to solve for a. And we'll go through an example of what that looks like. We have to actually solve for that. For exponentials, y equals a times b to the x. A here is the y-intercept, and b represents the common ratio. So we have to be careful here with linear functions. B represents the y-intercept, but for exponential, b represents the common ratio. So let's look at table number 1. Okay, looking at table number 1, we know the x values are all increasing by 1, and what's happening with the y values? Well, to get from negative 1 to 1 was plus 2, plus 2. So again, this was the same table on the last slide of notes, and we determined that this was a linear model, right? A linear function. So now let's write an equation for that data. The equation for a linear function is y equals mx plus b. So the m represents the slope. Okay, what's happening with our x values and what's happening with our y values? So let's find the change in y over the change in x. So what's happening between the y values? Well, we are increasing by 2. And what's happening with the x values? We are increasing by 1, so the slope is 2. So I have y equals 2x. Now, to figure out the y-intercept, just look at your table and determine when x is 0, what's y? Well, y here would be 3. So I get y equals 2x plus 3, and that equation would fit the data that is in the table for a linear function. Let's move on to table 2. Okay, table 2, again, the x values are increasing by 1, and in between the y values, we are multiplying by 1/3 each time. So this would best fit the model exponential. So for an exponential model, again, we have y equals a times b to the x, where a is your y-intercept and b is your common ratio. So here, y equals a is the y-intercept. So as I look at the table, when x is 0, what's y? Well, y is 4. So I have y equals, 4 times, and then my common ratio is 1/3. So 4 times 1/3 to the power of x. Now, I can test out my function if I wanted to by actually plugging in a point for x and solving for y. So again, let's just try like plugging in 1. So if I plug in 1 here, 1/3 to the first power is just 1/3. And 4 times 1/3 is 4/3, which would match the point when we plugged in 1 for x for the correct output of 4/3 for y. So it works. Let's go on to the last table. Last table here, we can see with the x values, we are increasing by 1. And in the y values, Let's double check this. Again, I know this was the same table in our last example, but let's just go through it one more time so we make sure we really got it. So between 32 and 18, we're subtracting 14. Between 18 and 8, subtracting 10, subtracting 6, subtracting 2. Those were the common first differences, but now if we look at second differences, we have plus 4, plus 4, plus 4. So again, this is a quadratic function. So now we need to write the equation y equals a to the x. Y equals, ax squared. Y equals ax squared. Now, I have to actually solve for a here by plugging in a point and figuring out what a is. So I'm going to choose an easy point. I'm going to choose -1, 2. Now, Ms. Roddy, why are you not choosing 0, 0? Well, think about it. If I plug in 0 for x, 0 squared is 0. 0 equals 0. Doesn't tell me what a is. A cannot then equal 0. So that would not get me anywhere. So you can plug in any point you want from your table, not 0, 0. That's the only one you cannot plug in. Why? Again, it won't get you anywhere. So let's plug in -1, 2, because I want to use the smaller numbers, the better. It's going to be easier. So what this looks like is I'm going to plug in 2 for y. I'm going to leave a as it is. And I'm going to plug in -1 for x. So again, I use that point right down here. Now let's do the math. -1 squared is 1. So a times 1 equals 2. Okay, now let's solve for a. Well, it doesn't matter if we try dividing by 1. It doesn't even matter. A equals 2. So my function, then I'll plug 2 back in for a here and get y equals 2x squared. Now again, I could go in and plug in any point that I want and make sure it works. So let's go back and look at our table. Let's say I want to plug in -3. So here this would look like 2 times -3 squared. Well, -3 squared is 9 times 2, and that equals 18. Was that the output when I would plug in -3 for my table? You bet right there. So we know that that equation will work for this table of values. So again, what we did here is we first determined which model fit the data by looking at the tables. Then we plugged in information to determine which parts of the equation we needed to figure out, and then we wrote an equation for that data using either a linear, quadratic, or exponential model. Thanks for listening. Have a great day. Bye.